Okay, so let me start by presenting this first slide. So on this slide, I have pictures of a number of different types of price discrimination that you may be familiar with from your daily life, which you probably are familiar with. And these different types of price discrimination have something in common, and that is that they have one or the other of two characteristics. The first characteristic is that many of them rely on self-sorting. So they won't actually explicitly charge people different prices, but they'll offer some sort of a quantity discount, and people who care more about the item will buy a larger quantity. The other characteristic that some of them have is they do explicitly charge people different prices, but it's based on some very simple characteristic, and it's also something that can be easily verified. So an example of this would be a student discount. They can verify that a person's a student because they have to present their student ID card. Now, while these pricing strategies can raise profits, and presumably do because they're so common, they don't extract nearly as much profit as is theoretically possible. So there are different papers that look at this. I had a paper with Joel Waldfogel that looked at MP3s, and we found that these strategies can extract about a third of the theoretical maximum profits. Now, first-degree price discrimination, or person-specific pricing, can theoretically extract full surplus. So if it's perfect first-degree price discrimination, if you would charge each person their exact willingness to pay for each item bought. There's also imperfect first-degree price discrimination, where if the firm doesn't know exactly how much to charge a person, they can still charge people somewhat different prices and raise expected profits, even though they're not extracting each person's full valuation. So these different forms of price discrimination have gone back in the literature for a long time, at least in theoretical literature. And in my class, and I think it's somewhat common, that when you're teaching price discrimination, you start out with first-degree price discrimination, then say it has all these great properties, it's the best strategy to use, but you can rarely actually use it because you need to actually know how much a person is willing to pay for your item. And that's usually their private information. And it's not only the way it's taught; it tends to be it tends to be true. So it's rarely seen in practice, and there's very little empirical work on it. So while it's historically rare, the advent of big data, basically a large amount of data collected on individuals, could potentially reveal some information which could be used to glean their valuations, which might allow firms to do so. So this is something, this is actually something I noticed after I started the project. So at my local grocery store, if I give them my Stop and Shop card, they'll, I don't know if it's an app that they have too, they also have these little scanners, and it'll give you your exclusive offer. So they'll basically offer me and only me, well not only me, but they're not offering to everyone discounts on specific items. Now this is not the exact question I'm looking at. What I'm going to be looking at is how useful web browsing data is in predicting how much a person is willing to pay for an item. And there are three main goals in my paper. So the first goal is to determine how much web browsing data can raise profits for a specific product. I'll talk about that more in a second. And then I want to estimate the impact on welfare and equity. So I'm not going to really take a stance on it, but by showing the distribution of prices that different people are charged for the same item, that will potentially inform on that. And then the third goal is to adapt machine learning techniques to the order of choice framework to be consistent with the way, the setup of this problem. Okay, so the context that I look at is Netflix, and there are three main reasons why. One is that Netflix did sell online. Basically, all of their sales are online, and so they could presumably use web browsing data to tailor prices. The second is that they seemingly can implement price discrimination. So there are a couple characteristics that you need to, or a couple things that need to be true about the product and the level of competition for them to be able to price discriminate. And the fact that they do currently second-degree price discriminate seems evidence that they could, in fact, charge different prices to different consumers. And the third one was key. So I needed to get a data set to analyze this problem that both had individuals' purchases in the data, So I had to know whether each person was a buyer or subscriber to the item. And I needed to have a lot of information on their web browsing behavior. And so Netflix allowed me to find a data set that had both. Okay, so the general research strategies, I'm going to break it down into two parts. In the first part is something I can verify in a holdout sample. In that part, I'm just going to look at how well different sets of variables allow me to predict whether or not someone is a subscriber to Netflix. Just a binary variable. And so first I'm going to look at standard demographics. Standard demographic variables are types of variables that presumably, when a person walked into a store, a salesman might have been able to glean from their appearance, their accent, other things that they might be able to notice in face-to-face transactions. And then I break the web browsing data into basic web browsing behavior. I'll explain what those variables are later, and visits to particular websites. And the idea about the websites is that they might contain several types of information which could be useful for figuring out how much a person was willing to pay for that. So it could reveal direct interest in related products. That's one way. It could also reveal sort of unobserved demographics. So, for example, most data sets will not have things like sexual orientation or marital happiness or a whole host of other demographics you could think that might correlate with a person's willingness to pay for an item. Now, while it's not normally collected, presumably a person's web browsing behavior might at least partially reveal those characteristics. So I'm going to look at these three sets of variables, and then the second analysis, which I can't verify in a holdout sample because I did not actually observe Netflix charging different prices. So it's a structural economic model, and that shouldn't cause any problems, but it's the reason why I split it up into these two. In the second analysis, I actually simulate the gain of profits from using this strategy, comparing it with the gain of profits using the strategy if you only use demographics. And then I also look at the distribution of prices that would be charged. And so let me give a quick preview of my results here. So the probability that an internet-connected household or internet-connected user subscribed to Netflix in 2006, the year they have the data for, was 16%. If you then try and predict based on demographics, you find that the probability in your predictions varies from 6% to 30%. Now, if you had perfect predictions, remember everyone would be 100% or 0%. So the wider the distribution of probabilities based on your model, the better it is able to predict. When I throw in all the web browsing data, the range of probabilities increases much more. It ranges from basically 0 to 91%. So based on all of this data, for some people, I have a very good idea about whether or not they are a subscriber, and that's information that could be used to figure out whether we should offer someone a lower price or a higher price.
Can you, just to flesh out, like I said, the second point, the demographic predictive probability. So, for example, a male, age 65,
Yeah, so there's age brackets in my data, but yeah, it's gender, income, kids, race, let's say age, it's also region. So there's a good number of demographic variables in the data, sort of the typical set of demographics you would observe in these data sets. Okay, and so when I look at the second analysis, I find that I'll talk more about the interpretation, at least my interpretation of the magnitudes, but clearly when only demographics are used, adding first-year price discrimination to the prices you're already using raises profits by 0.14%. So it's very small. When you use all of the data together, I find that they could raise profits by 1.4%. Now, I don't know if that's big or small, but clearly it's a lot bigger than what they could yield based on demographics, and so it's a lot more likely that firms would in fact use it. And so that sort of leads me to the second question is, what is the impact on consumers? What are the different prices or the distributional impacts? So I just want to mention before I move into my results, or into the next steps, that I showed the example for Stop and Shop. This actually seems to be the tendency for firms to use this strategy seems to be picking up. So I talked to a startup firm which is now doing online pricing for 3 firms which have a market cap over $1 billion. I think these are decent sized firms for using. They're actually only using customized discounts, but they are using a subclass of the strategy. Okay, so let me talk a little bit about the data that I'm using in this. So I use the ComScore data. I don't know if any of you are familiar with it. Basically, it tracks everything that some people do online. So it tracks about 60,000 individuals for the full year. It has the top level domain for every visit that they have, the time of that visit, the duration of that visit, the number of web pages they looked at on that web page. It has all of the transactions that occurred in those visits. And it also has a referring website, and importantly for this analysis, it also has the demographics of the individuals.
What's their inducement to participate?
It's a little bit mixed. So I guess some people intentionally downloaded the software that tracks it. There also were a number of stories about it basically piggybacking on other software being downloaded. So some people might not have been aware that they were installing this. So it's sort of mixed in that way. I don't know what percent is each. Okay, so the first thing I did is I aggregated it to a cross-section. So I first dropped a bunch of websites. Now some of these websites that I dropped we might have wanted to keep, but I basically came up with an algorithm that dropped some websites I did want to drop. Yeah?
Sorry, do you know in this research who's a Netflix subscriber and who isn't?
I impute it, and I'll talk about that.
So Netflix isn't giving you that, never gave you that information?
No.
Okay.
No. Yeah, I'll talk about that just in a minute. So first I dropped a number of websites. So it's pop-ups, and there's a lot of pornography actually on there. That might actually reveal what someone's willing to pay for Netflix, I don't know. But I just dropped the whole class. And this is sort of at least a starting point for it. Okay, and so I said it's a cross-section, so I have the number of times people use each of these 5,000 websites that stayed after, that remained after these, after removing a number of them. Also, when people tend to use the internet, we'll talk about that more in a second, and internet use intensity. And then the third thing that I did to the data is I imputed whether or not someone was a Netflix subscriber. So for some people in the data, they purchased it during the year on the computer that was monitored. And so for these individuals, I observed exactly which tier of Netflix they purchased. For the remaining users, I did not observe them buying it, so I had to impute whether they're a Netflix subscriber. Now, I assume many of you have subscribed to Netflix. So if you do, you have to update your queue every so often, or you don't have any more movies sent to you. And so to do so, you have to explore movies, go to different pages within Netflix. And so a Netflix subscriber has a good deal of motivation to actually go to many pages within Netflix, many of the sub-pages within the top-level domain. People who are not Netflix subscribers do not. So I assume that anyone who averages more than 2 page views per visit is a Netflix subscriber, and anyone who does not is not. And so I've done various tests changing this a little bit, but it seems to be a pretty good way to aggregate it.
Was this pre-streaming?
This is pre-streaming, yes, 2006. It started early to mid 2007, so there's no. And so by this imputation, it actually matches up quite well with my estimate of the number of Netflix subscribers I would expect in the data based on auxiliary information. Okay, and so here are the 3 classes of variables. So that basically I'm going to compare how well these different classes predict Netflix subscription. So the first class these are the list of demographics, and as I said, these are things that you might be able to figure out if you're, say, a car dealer and trying to figure out how much a person willing to pay. The basic web behavior variables. So internet use intensity is a measure of how comfortable people are on the internet, how often they use it. I also have a couple other things, number of unique transactions, other things like that. And then I have browsing by time of day and day of week. So it's hard to know exactly what might predict whether someone's a Netflix subscriber, but for something like DVD ordering or DVD by mail, presumably some people might have a harder time making a good blockbuster, and so this might indicate or help predict whether someone is a Netflix subscriber. And then the last set are the detailed web behavior variables. That's a number of visits to each website, and there are almost 5,000 of those variables. So I'm going to have to use some machine learning techniques to deal with a large number of variables there.
So a lot of people who are visiting the web are doing it at work. They're in the comp store set.
So it tracks one computer. It's supposed to be the home computer, sort of what their goal is, but it's, I don't know if they're sometimes tracking work computers or not. So I will not pick up anything on it that the person does on another computer. There are better data sets available now, though they're very expensive, but I think Nielsen has data. They also there's a paper showing that people's web browsing behavior is fairly stable over time, and it can well predict who the person is. Okay, so this is the first step that I was saying. I'm going to show how well these different data sets predict whether or not someone is a Netflix subscriber. So first thing I do is I just run some ordered probits. I mean, not ordered at this point. I just run some binary probits to predict whether or not someone is a subscriber on the demographics and then the demographics and the basic web behavior variables. And so the main takeaways that I have from these regression results are first that adding to demographics the basic behavior variables increases the likelihood quite a bit. Now there's a lot of observations, but it's significant at, it's basically, the p-value would be so low as to not be distinguishable from 0 by machine precision. And the second thing is once you add these basic web behavior variables, some of the demographics drop out. So the idea here is, at least the way I view this, is that the demographics are a very rough, a rough approximation of some information, which is better captured in the basic web behavior variables.
That's the entire set of variables that...
No, these are, I only show the ones that are significant. So there are others that were not significant. These are the entire set that were significant.
About how many in total did you have?
I had different race and ethnicity dummy variables, income groups, which is put linearly, age, household size. I had the population density from, I had, I think I...
You had the IP, the geography?
Yeah, I think that's what it was. I added it in from census and then the census region. And so you can see, and so there are more demographics of web behavior variables, but a lot of the web behavior variables were significant. And so, for example, here I do find that the percent of use on Tuesdays and Thursdays is a predictor of whether or not the person is a Netflix subscriber.
Okay, why are some light colored and some are dark colored?
Oh, it ended up that maybe it wasn't the best way to present it. I was just trying to make it clear which corresponded to what.
Some are significant.
Yeah.
They're just alternating.
They're just alternating.
Yeah, there is a pattern.
Just for, I apologize if I came in a little late. Do you know who the person is? Do you know who these people are?
I don't have a name. I know their demographics. That's all I know about them. That and their demographics behavior. Okay. So the next step was to start to add the detailed web behavior variables, the number of visits to each website. And so the first thing that I did was I just added them one at a time. So basically, I just want to see how well each website does on its own in predicting whether or not someone is a Netflix subscriber. And so I added them to the demographic and basic web behavior variables. And then I computed the p-value. So the p-value of 5%, we would expect if they're completely random to occur 5% of the time. I find that 29% of the websites are significant at the 5% level. So far more than expected by chance, which suggests there is some actual information in these websites. They are actually helping predict whether or not someone is a Netflix subscriber. Yes?
Just because, so when you say a website, so website A, if it's visited, then it's a website that predicts greater likelihood of being Netflix.
Well, I have the number of visits is the variable, but I've tried different specifications.
Also,
Are most
the
of them
number of
zeros?
visits to website A.
Most of them are zero. Well, for the popular websites, most of them are zero.
Well, how many websites are you adding in there? Are you checking? In the set, the 29% of how many?
5,000.
5,000. So
Some of them
the
are
5,000
yeah.
most popular sites, basically.
Yes, the same,
Okay.
essentially. Yeah.
And most of those aren't zeros.
No, so when you get to the less popular ones,
Oh,
most people don't visit those websites anymore.
right.
So I did try also just putting in a dummy variable, but I guess I could have some combination. Presumably, when you're running these different models, you could try for each variable a couple different specifications. You could have just a binary variable,
Yeah.
a number. You can have both in there. Okay. The next thing I did is actually after doing this analysis, I was just curious which websites are best predicting whether or not someone is a Netflix subscriber. And
And they can predict in either direction. Sorry to interrupt, but like, so there's a bunch of zeros, and then I went to website A. Is that usually a positive predictor?
it's usually a positive. So the top 20 are all positive
Yeah.
predictors, but it could principle be either. So all of the 20 that best predicted, or most significant, were all positive predictors, and intuitively they seem to make a lot of sense. So there are some websites which people who are movie lovers would typically go to. So IMDb and Rotten Tomatoes are examples of movie review sites. You also see a number of sites where people would tend to order stuff by mail. So Amazon and GameFly. So GameFly is basically is Netflix for video games. I'd sort of call it internet savvy. I don't know whether that's more of my opinion. Discount shoppers. So you see a number of discount shopping websites because you can on Netflix you can return them quickly and get a lot of DVDs over the month. And then rare products. So I guess this is a site which I didn't know before I started this, but it's a site where you can go to get rare books. And Netflix, because it was it's mail ordering, they have large warehouses somewhere. They typically had a better selection than Blockbuster. So basically, the point of this is that which websites are significant tends to intuitively make a lot of sense. So the next step was to add add the websites together. So this is just adding them one at a time. I want to get their joint prediction. There are a number of problems that tend to result when you have a very large number of explanatory variables. And so I list a number of them here. So insufficient degrees of freedom. Here I actually have more observations than variables, but it doesn't have to be the case, especially as you increase the number of variables or if you have a small sample. Overfitting can be a problem, particularly if some of the errors are correlated across individuals. And tractability and convergence, so if you throw a lot of variables into a model, it may not actually yield a global optimum. Computer memory limitations are something I actually was running into this. I had a pretty fancy computer that I was using for some of this. And you very quickly run out of memory when you have 60,000 individuals and 5,000 variables, or you increase that even further. And then missing data, so a lot of, I don't know, at least Stata, I didn't use Stata for this, but at least Stata drops. So if you have an observation, if any one of the variables is missing for the observation, it drops that. And if you have a large number of variables, it could be that any one observation tends to have at least one missing variable, and so it would be dropped from the overall regression. So these are a number of problems that occur. Model averaging, basically taking the average of the predictions of many smaller models, you actually weight them, but taking an average of predictions from many smaller models helps address all of these issues. And so that's a strategy that I am using here. So first I just want to quickly just review, for those of you who haven't thought about it for a little while, the standard order binary probit model. So your dependent variable is binary, and the idea is that there is an unobserved underlying variable, which if it exceeds some threshold, the consumer, let's say, subscribes to Netflix, and if it doesn't exceed that threshold, they don't subscribe. And so you can calculate the probability. Basically, this is the based on your model, the best estimate of the underlying variable And this is the threshold, and so basically it's the cumulative density of that difference. And that gives a probability someone subscribes. Okay, and so here's just basically some details of the model averaging. Basically, there's some variables that I keep in all the regressions because they're deemed to be highly likely to be important. And then there's a second set where I'm basically drawing from in each of these, basically I'm rerunning these models many times and taking the average of their predictions. And the large set of variables were the websites. I don't know which ones are expected to be significant. I expect that the majority of them, or about 70% at least, will not be when added together. So this is that second set that are only included in some of them. Okay, so there's a yeah.
So I'm still a little confused about how this model averaging works. It seems to me the biggest problem is the overfitting, which is essentially data scooping, right? So we want to predict stock returns, and we look for everything we can think of. Does the company begins in A, B, C, D?
Yes.
The second letter, what's the second letter of the company's name? Is it a Monday or what day of the week? We just come up with. Eventually, we're gonna predict stock returns based on all these, based on looking at 10,000 different things. We're gonna find. But of course, if we do it again next year, it's not going to work.
Yes.
So I don't understand how this method is going to, and I would think that's the problem here. You have all these different websites, and we're going to find something. If we keep 5,000 websites doesn't do it, we'll have 10,000 websites.
So for any given model, so suppose you draw one set of variables, how well it predicts is either going to be overestimated or underestimated. And when you average over many models together, so actually the way this is traditionally done is in a Bayesian framework. So basically it's a Bayesian model averaging. By basically averaging over many models, some overpredict, some underpredict, but it helps deal with the model uncertainty. Is that sort of?
Yeah, because let's say I've got 5,000 websites.
Yes.
And, randomly I find out that 5 of them are really good. 5 of them, predict whatever, Netflix.
Yeah.
Okay. Now what am I going to do? I'm going to take 5 others randomly out of the 5,000 and average those two? What do I do?
No, so the way you traditionally do it is you have some sort of a prior, and then you calculate calculate the posterior probability of that model. And the traditional way is then you average them in proportion to the probabilities.
Well, let's say I have a diffuse prior. I don't know anything about websites.
But let's take an extreme version of logic. Suppose that we knew in advance that these are completely uninformative variables.
Right.
Suppose they were just random noise. We knew that, and we knew they were not going to predict into the future. If we did this, wouldn't we still be able to predict subscriptions on this set? Even?
Yes. So I guess you. So the idea. Okay. So let me respond a couple ways. So one response is the way I weight these models is I weight them based on their. So I figure out the weights based on. So I have a number of different models that have different likelihoods in the sample that I'm estimating it on, and I also have a holdout sample. And I figure out how much to weight models, how much to weight the most likely models to the least likely models based on sort of the overall prediction based on the average in a holdout sample. So one response to your question is if they had no information in the holdout sample, I would predict that all the models are equally likely, and I find that there is improved prediction. The models are more likely. This procedure would put more weight on it, looking at the holdout sample.
But in Eric's example, it's just randomness that's going to make one model or 2 models appear more likely. It's just random that these 5 or 10 websites out of 5,000 happen to correlate with Netflix subscriptions, even though there's no real causality. We're always going to get that.
Yeah.
I mean.
Okay.
Doesn't Doesn't the holdout sample deal with that?
Well, I don't, maybe, I don't know how, I don't quite see that.
To do it, well, I mean,
If it also predicts the holdout sample, that gives
Oh.
us more confidence, doesn't it?
yeah, unless you snoop and data mine.
So maybe I'm having trouble with the best way to respond to this because I don't tend to do bits. I'm not a Bayesian by training. Maybe I could return this later. I also do some actual tests to make sure that I'm not over-predicting. But maybe I should return to it in a couple slides.
Jeremy, you
Eric
know
and
this.
Andy keep staring at me, so I should. So machine learning is my thing, and I've done a lot of research on this.
Just remind us who you are again.
I'm the startup right in San Francisco, but I run a machine learning competition platform, and I just do tolerate claims as well, but I do machine and I guess this area of creating ensembles with workloads is my main technique. This has been very heavily studied in the research. There are indeed methods of getting large sets of models which you can leverage together. Generally, this is designed with a very badly. If you create each of the models in a way which is contains no systematic bias, each of the models is independent, and each of the models cannot fit themselves and fit the data, then it turns out that the average of the model does have the property there asked about, which is if you have a random bunch of variables, none of them are going to be predictive when they're under variables that are. One of the most well understood uses of this particular technique is what's called random forests, which Leo Bryman developed in 1999. In 2001, he showed that an analysis with just 81 rows of data and 64,000 columns successfully found the correct 15 variables. Exactly. So I don't know about this exact method, and I guess I was turned up here, so I'm sorry if the advice is not appropriate, but my advice would be there's a lot of well-understood techniques for using machine learning, but you might want to consider this is one of the more off-the-shelf ones because there's been quite a bit of research about how it is.
You mean like the Bayesian model averaging or something?
Whether it be Bayesian model or boosting or bagging or
Okay.
consultative decision trees or gradient boosting machines or whatever. It's kind of
So
a solved problem.
So bagging is sort of using a holdout sample to, right? Is that?
Yeah, so there's many different ways of doing it.
Yeah.
But basically, for example, the random forest, which is a bagged decision tree approach, uses many separate random samples and uses a holdout, not a holdout sample, but each one of those effectively ends up with its own holdout sample. So effectively, you end up with like 10,000 weird words.
Yeah. So the bagging, the problem with bagging is that you have to rerun the model many different times for a large number of different samples, or at least some number. So for each model, you have to rerun it a number of times. And I could try and do that. It takes, actually, to run the number of models that I did, it actually takes over a week to do, even. So the problem is, I guess I could run more and I could have more parallel processes, but I haven't done that yet.
There are very optimized ways to do that.
Okay.
So, for example, I've got something which ran, I think, 100,000 models on a data set with quite a few 100,000 rows, which took something like 12 seconds. Like, we're really.
Okay, and this is not regression, this is something else.
No.
Okay, I'll take a look at that.
The other thing I wanted to mention, just if you want to come back to it, this is really idea. I spent 10 years creating a startup, which did per user-based pricing by calculating upside rules and payment profits.
Okay. I definitely would like to hear that. The only other thing I'm going to mention about this is sort of that the Bayesian model averaging maybe there's a longer history of it, and so it's more established. For Bayesian model averaging, there exists an analytic formula to integrate over the values of the parameters in each model. And that's the way you're supposed to do that. For the ordered choice model, or for a binary probit, I'm not aware of analytic expression for the overall probability of a model. And so that was sort of another reason I diverged from the Bayesian model averaging approach and used the holdout sample to come up with the weights. Yes.
I don't want to belabor this. I'm not a machine learning expert at all, but I don't think this is. I see machine learning as, as you said, it's a true model. Every model, the assumption is there's none of the models are overfit. It's a true model. The machine learning is the way to get to it. The problem here is the data snooping problem. And that's the issue that I can't see.
Well, so there's an important distinction here between prediction and figuring out which variables are the true variables.
Sure.
Okay.
But the prediction won't work if you then wait a year and do it again, or wait 5 years and do it again.
Well, so let me show you in just a couple slides when I actually test it on a holdout sample and I find it actually does fit quite well. So maybe that will help address some of these concerns. Okay, so let me just quickly talk about a problem with using model averaging in a binary or ordered choice model. So let me start with a quick analogy. So suppose that you go in for a medical test and you're getting a test for a certain disease, and they give you 3 separate tests. So basically these tests are separate signals for whether or not you have a disease. These 3 separate tests are sort of like 3 different models that I'm running here. If all 3 come back positive, let's say each one alone predicts that you have, let's say, cancer with a chance of 0.9, the overall probability combining the information from those models should yield a probability that you have the disease of over 0.9. In a Bayesian model, in this model averaging approach in an ordered choice model, it actually yields the same probability as any one of these single tests, 0.9%. So it's not capturing the joint information. Right, so here's basically the underlying reasoning. So in a binary probit, the probability that a person has some outcome, it's exactly depends on the difference between their estimate of their underlying variable and the threshold. And so if all 3 have a 0.9 probability in these models, because the standard deviation of the error term is normalized to 1, they all have exactly the same value of that difference. And so if you average that difference across the 3 models, you're going to get exactly the same value, which predicts exactly the same probability. Now, the problem that's occurring here is that when you average across these models and getting sort of combining the information, what should happen is that the standard deviation of the error in your prediction should decline. Now, in binary probit, it's normalized to 1, but you could just let the standard deviation. You could estimate the actual standard deviation afterwards, after you've combined the predictions from the models. Another very easy way to address this is actually just to include each person's estimate of their underlying latent variable minus the threshold as the only explanatory variable in a new probit model. And then that will allow it to use the data to figure out how much to scale it up. So that's the procedure that I use. Okay, so this just talks about how I weight them. Basically, I just figure out, I parameterize how much to weight the more likely as opposed to least likely models, and I estimate that. So let me move on here to, so this is my evidence that the model fits. So what I do here is, based on my model's predictions in a holdout sample, I order individuals according to the model's prediction for whether or the probability that they subscribe to Netflix. I then put them in groups. So I put them in 200 groups. And the first group are the 0.5% of people least likely to subscribe to Netflix according to my model. And then I create a number of identical groups. And then for each of these groups, I calculate the average probability that they subscribe according to my model, and the actual observed probability, basically the fraction of them that consume Netflix. And so I plot these 2 against each other. So the dots are the actual probability of a group, and the blue line is the predicted probability from the model. And this is all done in a holdout sample. So I don't know if this helps address your question.
What's in the holdout sample?
I had 60,000 individuals. I estimate the model on 30,000 of them, and then this is done on the other 30,000. Okay, so on this plot, I'm basically plotting the predicted probabilities for from the model for different sets of explanatory variables. And so this red line is when all the variables are used, the green line is when just the basic web behavior variables and demographics are used, and here's the demographics. So you see this black line, which I didn't mention, is the uninformed probability that anyone subscribes to Netflix. And as you see, as you add more and more information, the range of prediction goes up. And so for some individuals, the probability that they subscribe to Netflix is as high as 0.91, and some people, their probability is essentially 0. And you can see also differences, not just in the most extreme, you can also see them at different percentiles of the distribution. And so this sort of
So just a small nuance. I mean, you're not literally predicting how well likely they are subscribed to Netflix, but how likely they go to those 2 pages, two or more pages at Netflix.
On average, yeah.
Right.
I've tried different specifications and it comes out fairly similar, but yeah,
Right.
I have.
I mean, it could be that you get really good at predicting people who click on lots of pages or something like that, and the Netflix subscribers, you start getting potentially more and more of an error if you're picking up some other.
Yes.
If Netflix, there's some Netflix subscribers that click a lot and some that don't click a lot. You're gonna be
Yeah, so it's possible.
tightening that error.
That is correct. So I've also tried a specification where I say they have to average more than 2 per visit and have to go to at least Netflix at least 20 times over the year. It's possible that there's some people who are not Netflix subscribers who are doing that. If people are clicking on a certain link to Netflix or tend to click on ads to Netflix, when they click on the ad, especially if it's they've already visited Netflix before, they're probably just going to look at the one page that their ad goes to or go to one other page and then close out of it. But I can't rule that out. That is correct. That was actually one of the main challenges of this research question is how do I find a data set that both has information on whether or not they're buyers of an item and all their other information, browsing data. And so, yeah, I can do other robustness checks for that. Okay, so this just illuminates that even within, so this red line here, it's basically the same thing, but for just people who are predicted to have the lowest 10% probability of consuming Netflix according to demographics. So this just shows that there's still a lot of information lost so some of these people based on demographics have very low probability, but in fact some of them have a very high probability, and the web browsing data is able to pick that out. Okay, so let me explain the structural model that I use. So let me start by explaining behavior. So there are a number of different tiers of Netflix that one could subscribe to. You could subscribe to, there are a couple limited plans where you get there's a limit both on the number of DVDs you have at a time and the number that you can receive each month. These were pretty unpopular, so I assumed that anyone who purchased one of these would have subscribed to one of the unlimited plans, which places no limit on the number that they'll send to you each month. It just places a limit on how many DVDs you can have at one time. There were 4 unlimited plans, 1, 2, 3, and 4 DVDs at a time. Almost no one in my data who I observed buying bought the 4 DVDs at a time. So it's mostly these first 3, though that doesn't actually really affect my analysis at all. I could have anyone who bought the 4 DVDs at a time from the standard theoretical models would have bought the 3 DVDs at a time had the 4 DVDs at a time not been available. And so, okay, so you can basically see these 3 options. So the idea here is that people differ in how much they like DVDs by mail. And so if you don't like it very much, you won't subscribe at all. If you like it a little bit more, you'll get 1 DVD at a time. If you like it even more than that, eventually there's a point where you'll consume 2 DVDs at a time, and so on. And so I'll talk about very briefly about how I derived this model. But basically, this is the intuition behind the model. So on the x-axis here, I have well, it's not actually the individual's valuation for quality. It's actually the error in my estimate of the person's valuation for, here it's labeled as quality, but it's DVDs by mail. And this red line gives the probability density function of that error term. If the error is high enough, if it exceeds this first threshold, the person will be willing to buy 1 DVD at a time as opposed to no DVDs at a time. If it exceeds a second threshold, they'll be willing to buy the 2 DVDs out of time plan as opposed to the 1 DVD at a time plan, and so on. And so the probability that a person subscribes to the 1 DVD at a time plan is just the area under the probability density function between these 2 thresholds. Now what's happening in my model is I'm predicting how these thresholds vary across individuals. So if a consumer, let's say, visits celebrity gossip websites, which indicates that they like movies and are more likely to subscribe to Netflix. In my model, what that will do is that will shift all 3 of these thresholds further to the left. Also, if the price of one of these tiers goes up, it will shift the threshold to the right. Now, I derived this from the Musa and Rosen sort of standard second-degree price discrimination utility function. So basically, the utility is equal to the valuation for that type of product. That's basically how much the person likes DVDs by mail times the quality of the tier, plus the price sensitivity times the remaining income that they have after buying this plan. And it's getting a little close to 1, so I'm not going to go through all the details, but basically I replace this variable with the regression expression. So I'm estimating that value for all these different individuals. The income term just drops out. Okay, so some details I'm going to skip. One problem that I ran into is that Netflix, well, actually, I guess it has its advantages and disadvantages. Netflix did not change its prices over the period analyzed. So I don't have in my data the variation needed to estimate the price sensitivity. And so what I do is I basically estimate it afterwards. So I find what level of the price sensitivity would yield predicted optimal prices, which are very close to the observed optimal prices.
So this is kind of the opposite of my earlier question, but could you tell from them visiting the sites which ones subscribe to 2 or 3 versus 1 by like which page they clicked on?
I tried to do that a little bit. I have a very small number of individuals who I observe them buying, who are choosing a Netflix plan, and I tried to use it. I know there's a slight correlation, but not enough to do with much accuracy. Okay, so let me move on to the results. So basically, I estimate the model. I get my prediction of the underlying variable for each individual.
Well, actually, so aside from what they pay for, you could probably get some sense of the intensity of Netflix. Like right now, you just have a binary variable, either Netflix or not Netflix. You could probably get a sense of how intensely how much time they spent on the Netflix site and whether they were frequently updating their queue or adding.
Yeah, so there are differences in how often people update their queue. But it's not necessarily that how often matters. I guess I could look a little more into it. Some people might arrange their queue with 1 visit for the next 6 months, and other people might come back every week to sort of change it. So there are some difficulties with that, but that is something I should explore more.
Don't you risk getting entangled with the difference between the household's use of the subscription and the individual's use of the single computer that the data is coming from?
So you're saying that there could be people going onto Netflix from another computer. That is something I don't measure.
Well, more than the subscription to Netflix is a household subscription. So,
Yeah. I'm not sure that's so if
this
there's
is
one
specifically for the DVDs that it's playing.
Yeah, so if there's one sort of family computer, and
But it's more likely to be individual computers at one Netflix subscription, which may be multiple DVDs at a time.
okay, yes, so that might be a reason why it's not showing up in my data. Is that a family might subscribe to the plan? That you can give individuals in that family their own queues to update, and I might be measuring only one of those queues. So that's a great point.
Or even if there's only 1 queue, even if the family shares 1 queue, different members of the family from different computers can be accessing Netflix and moving stuff around in the queue, and that's the problem. It's not, these decisions are not, often they're not an individual, it's a family decision.
Oh, yes, yeah. Yeah, so I guess I might not be measuring it might be a family decision, and I'm only monitoring one of the computers. That's sort of saying something. Yeah, so that might be why it's very hard for me to figure out which plan they're on.
Right.
Well, this is 2006 data, though, right?
This is 2006.
Okay, so we don't have a whole family full of people with iPhones.
No, I thought it was different computers.
Well,
Yeah.
but it's 2006. It's still, for the vast majority of households, it's probably still one.
I don't know if it's
But
necessarily
for
true
the
for
more
the vast
affluent-
majority of households that consume Netflix, though.
Yeah, that's the thing. You got about 1/6 of the households, it's probably the more affluent 1/6. So yeah, it could be more of a problem with general population change. But you don't have the smartphones things. You cannot run this today without getting like smartphone data because everyone.
Yeah, no, there's several reasons why I chose 2006. Actually, the streaming, I think that you asked about, was one of the reasons I chose 2006. So I didn't want that to confuse results. Okay, so this table summarizes the basic conclusions as in terms of the profits that are available. So this is, I sort of mentioned before, the increase in profits in first-degree price discrimination goes up quite a bit when you use all variables as opposed to just the demographics. So I also did a back of the envelope calculation.
So I'm confused there. Is there a surplus going up or down?
It's going up because the aggregate consumer surplus is going up. On average, so only about 16% of people subscribe to Netflix, and so most people are unwilling to buy at the price that they were charging. And if you're offering person-specific pricing, the majority of people are going to be getting a discount. And that might help explain that. The people who the price is raised to obviously have lower welfare under person-specific pricing than beforehand. And it sort of depends. Obviously,
It's kind of unusual. Usually, personalized pricing leads to less consumer surplus. At least that's the textbook.
yeah, well, I think it sort of depends somewhat on how well it's done, right? So maybe when I show you the price distribution, that might help clarify. Okay, so basically for Netflix in 2012, I predicted the strategy would raise profits by 15 million. Should be enough to implement this pricing scheme if they wanted to. But still, it's still leaving a lot of money on the table. Only 42% of the area under the demand curve is captured by Netflix.
This is to change the first degree from second degree or from flat pricing?
No, it's already second degree.
Okay, so
This
maybe
is
that's part
adding
of it.
first
Yeah,
degree.
right.
Yeah.
That can help explain.
Okay, so I also just calculated the same table, but only allowed them to give discounts from the profit maximizing second degree prices. So the idea here is that firms might be scared if they raise prices to individuals that would lead to some bad press. And so something that seems to be more appealing in people's minds, at least they don't get angry about, is giving certain individuals coupons. That is something that is already done. So I wanted to basically look at that. If we just give discounts from the profit maximizing sort of second degree price discrimination prices. And in that case, the profits go down some. They're about a third as high, or the gain in profits are a third as high. So it's 0.44% versus 1.4%. But still, you notice that the difference between the increase in profits based on just demographics and based on all variables is quite different. So regardless of whether this is large or not, it makes it seem that firms will be much more likely to actually implement this strategy now that this other data is available. And again, the consumer surplus actually goes up even more because no one's having the price raised. So that, yeah, Shane?
Yeah, so the demographics, all variables change. So is that going to result in neighbors paying different prices? So this concern that if it's one thing, if what's driving that difference is everybody lives in the same neighborhood because they have the same income, a lot of things cluster in geography, so you get the same type of people with the same taste and the same income and the same education in the same area.
Yeah.
In this case, they aren't really charging different prices to people who live nearby. But if the first degree or the movement towards first degree, even with the limitation you're placing on it here, if that movement to first degree results in friends paying very different prices because they got different coupons
Yeah.
You run into this kind of interesting.
No, that
It's just I don't know. So I'm curious if that can you tell?
So I think I had the zip code, and maybe I could look to the correlation within zip code. I could try and do that. I absolutely see your point. So people sort into neighborhoods for all sorts of reasons. It might not just be income. There could be all sorts of characteristics that people want to live around people with similar characteristics. And if that's predictive, that would actually bode well for sort of not upsetting consumers. I haven't done that yet. That's a great suggestion. Okay, so here's the price distribution. So basically, I plot histograms of the prices that different consumers are charged for the one DVD at a time plan based on all variables and only demographics. And clearly, the distribution is much wider when based on all variables. Now, the black line actually gives the price without first-degree price discrimination. So you can see that the majority of individuals are receiving a discount here, and that partially clears. Now, some people are receiving higher prices, or decently higher prices. So this table summarizes it a little bit more formally. So here I plot the percentile of prices for different individuals. Now, I just want to say that these price percentiles and the percent difference from the uniform price that would be charged, or the price that was charged, it looks very similar across the different plans. So that this is the one DVD at a time plan. It looks very similar for the 2 DVDs and 3 DVDs at a time plan. So you can see that the median consumer actually gets a discount, and you can see that so the highest person, the highest price charged in this simulation, the person is charged 42% more than the price that they would be charged without first-degree price discrimination. The lowest person would be charged 29% less. If you combine these numbers, that means that some people are paying twice as much as other people are for the exact same item.
Although if you go with the 1% and the 99%, that truncates
it does shrink it some, yes. So there are some
There's
really
some
extreme
outliers.
values, yeah. So there's a question about whether or not this is fair. Now, so this is one set of data. So this is web browsing data from 2006, and there are fewer websites. There's also a lot more data that one could try and use to predict whether someone's willing to buy Netflix. So there's location data collected from smartphones, basically where someone is every minute of the day. You can analyze the text in people's emails, Twitter, Facebook, other things like that. And presumably these might also contain information which would relate to how much someone's willing to consume Netflix. So I basically wanted to see if you improve the estimate on a person's valuation for Netflix. This point here is about what the standard deviation of the estimate is in the data that I'm using, and you can see that it will very rapidly. The prices will diverge very rapidly as we're able to predict better and better. Okay, so I just wanted to quickly talk about the literature. So first-degree price discrimination theoretically is better than other methods, except for bundling, which under certain conditions can also extract full surplus. Though it often doesn't. Though I find that first-degree price discrimination also doesn't, because you can't perfectly predict it. There is a host of empirical papers that look at other forms of price discrimination in the econ literature. In computer science, there's one paper that looks at whether firms are charging different prices. So basically, it pretends to be a bunch of different computers with different cookies, different locations, etc. And they find that some firms, but not most, are doing some form of person-specific pricing. So Staples gives you a lower price if you're near an Office Max, for example.
So some of that made when Amazon got in trouble for doing this, they claimed that they were just testing random pricing, so it wasn't price discrimination.
Yes.
It was just experiments.
Yes.
So I don't know if that paper distinguishes that.
I think it was mostly discounts, but I have to go back and check. No. So I have to look at Staples. I don't know what Staples is doing, but I'll go back and check that. There are other websites that maybe came from a discount shopping website. That was the page you were on just before you went there. It gave you something like a 25% discount. But those were companies that people haven't usually heard of. Okay, so there actually was some work in marketing on person-specific pricing almost 15, 20 years ago. And what they did is they based the price on a person's past purchase history for that same item. And I think that's a very different type of pricing, and I'll explain why. So a couple of papers later, a couple of theory papers looked at what happens if you do this. So if consumers are forward-looking and you base the price that they pay next period on sort of whether they bought it this period at a certain price or sort of their intensity of use, consumers will anticipate that, and they'll basically pretend to be a low valuation type, and it doesn't actually raise profits. But if pricing based on these large amounts of variables, like in this paper, one, it's not clear that people cannot actually figure out such simple heuristics such as don't buy at high prices with bounded rationality, nor would they necessarily want to change all of their behaviors just to get a $1 discount on Netflix.
Right, but it does create some cost, because then they're going to start trying to figure out, how do I game it, how much time can I spend figuring it out?
Yes, that could limit it, yes. Yeah. And that's sort of, I guess.
Well, I mean, aside from being able to limit the price discrimination, it creates a lot of costs and annoyance on the part of customers.
Yes.
There's a way that I can get a lower price, I'm not quite needed. So there's a new kind of deadweight loss.
I guess there could be a deadweight loss. Though I guess a lot of people go to these. I mean, there are these price aggregation websites, and people still don't use it. People still pay higher prices than they could get at. Yes, Shane?
Yeah, if you apply the European Union's rules on privacy, which prevent tracking some kinds of web behavior, how much do you default for your ability to individually price? Because will it interfere significantly?
So that's basically they limit the tracking of all cookies, or is it?
Yes, some web bugs. So not cookies per se, but certain kinds of tracking devices.
I haven't done that yet, but that's
Because it's interesting. You can quantify the actual.
Yeah, the impact of that law. No, that's
Right.
that's very interesting. I will do that.
Catherine Tucker has a paper.
Yes, yeah.
I think we're just about out of time. If you want to say just closing, is that your last slide?
Yeah, well, so I have conclusions, but they basically, so I'm just going to mention one thing. So first degree price discrimination, the theory says that it's great for a firm. That's true when they're doing it unilaterally. If there's two firms competing and they jointly do it, it can actually lower both of their products, even though it's unilaterally beneficial.
Well, thanks very much. Appreciate that. So next week we're at Harvard Business School. I can't remember. Anyone remember who's speaking next week? Well, there's a seminar. Who's it? Laura Sheep. Okay.